All right, everyone, we are back, and we are going to be working on our solutions to problem set 3. So I'm working with a new novel alloy that boasts some very interesting Young's modulus properties. Population of the new alloy has a mean stiffness of 69 gigapascals with a standard deviation of 3. So we can go ahead and start to build in our functions that we may have to use here. So let's create our PDF equals 1 divided by square root of 2 times pi exponential of minus z squared divided by 2. Here we go. We also have, let's do our z function, which is going to be equal to x underscore mu underscore sig underscore set equal to x minus mu divided by sig. All right, so we need to calculate the 45, 76, 83 confidence intervals for this. So if we want to figure out which, if we want to figure out what's our 45% confidence interval, we need to do the following. We need to integrate our function PDF as a function of z of minus z1 to z1. And we need to solve for this equals 0.45 and solve for z1, although it'll solve it automatically. And we get this value. So we can now solve our basically z function, and we know we're trying to find our x, we're trying to find our mu, which is 69, our sig, which is 3, equals that value there. And we can magnify this here. We can just solve for it. And then we could also solve for the negative. Boom, there it is. 76 and 83. So let's go ahead. We can just do 76. We can just plug this in here. Here, minus, bang, bang, 83. You are hopefully starting to get the picture here. We got this. Bang, bang. Toot, toot. And then finally 95. 95. You should know it's 1.96. 1.96 minus 1.96. And there you go. So we've got those confidence intervals for this alloy. All right. So then we are asked actually, if you look it over here. So what percent of the data will exhibit a stiffness greater than 64 gigapascal? So I can do integrate, and then we are going to do PDF from our z function of our greater than 7. So we're doing 74, 69, and 3. And we're going to go from here to infinity. And let's look at it numerically. So that'll be my percent of a greater than 74. What else are we asked? How about less than 62? So we're going to go from minus infinity to 62. Less than that, minus infinity. And then there we go. What about greater than 64? Well, actually, I'm going to copy this one. So greater than 64. We can see that right here. What percent of the data will fall between 61 and those other values? Oh no, it's going to take me off screen. Nope, it'll just go there. All right. Let's keep moving. So we're looking at between 61, so let's just change this here, 61, and actually I'm going to copy this function, between 61 and 71. 71. So we can see that value here. And what about 64 and 70? 64 and 70 here. There we go. Excellent. If I make 837 measurements, so I'm going to do N3 is equal to 837. How many Young's modulus must be greater than 65? So again, we're looking at greater, so I'm going to do, actually I'm just going to take this 65, and I'm going to multiply this times n, 3. That would be the number of measurements there. Less than 74. 74 times n3. Good to go there. And greater than 71. So let's do 71 here. And voila. All right. If a sample exhibits a Young's modulus of 75 gigapascals, is that an outlier? So we said 69 plus 3 times our sig, which is going to be, our sigma is also 3. So is this an outlier? No, it needs to be greater than 78. What about 74? Or 64, excuse me. No, it needs to be less than 60. So neither of those are outliers. So again, it has to be greater than 3 sigma away to be outliers. Finally, 3 data files attached. What are the 95% confidence intervals for each of these data sets? Are they statistically significant? What do the distributions of these data sets look like? Well, we can go ahead and pull up. Let's go ahead and we're going to pull up these data sets. I believe they're in my downloads, D1 to D3. Boom, boom, boom. So let's go ahead and put those in documents. I am going to open up R, and we are going to open up a new script. I'm going to use our library tidyverse. And then I'm going to do library ggplot2, and let's see, library, I think we have just read Excel or maybe .csv files. Let's go ahead and actually let's go ahead and do, let's go over here. So let's go ahead and let's set our working directory. And then I'm going to go into, and let's do read.csv. Let's look at D1 first, d1.csv. Here we go. And we can kind of look at what we've got here. So we got a bunch of different X values and Y value. We just need the X value here. We don't need the number, the column here. So we're going to do, for example, I'm going to say this is D1 dat. I'm going to look at this. So D1 dat, I'm going to break it into, let's see what we got here. That will just be the rows. So I want actually the second column, my X. There we go. So I could look at, for example, I'm going to pipe this. Let's do pipe that to ggplot. ggplot, and let's go AES. Do I have this header here? Unfortunately, no. So I think I'm going to have to do just a single bracket too. This may break. AES, I'm going to say Y equals X for that axis plus geom histogram. Let's say, actually, excuse me, sorry, X axis is equal to Y. Now we're flipped. Why do you not like that? Let's look at our, let's look at this. D1 dat, D1 dat of 2. How does this look like? It's fine. Oh, is that X2? I think I labeled it as X. X equals X. There you go. That's confusing. But it's just the column header. Anyways, that looks pretty darn Gaussian to me. So if I want to do t-test, and I want to do t-test of my, this is now where I'm going to have to do D1 dat bracket 2 because I just want the numbers. And I can look at my confidence interval as such here. Now that I got that, I can just copy this data set and we can do this. I'm not going to change any of the verbiage. This is going to be very lazy. This needs to be 2 here. And I'm just going to go bang, bang, Bing. You can see the different confidence interval right here. Visualized. It still looks pretty kind of Gaussian to me. And then bang, bang, bang. Pretty Gaussian as well. And voila! We got it. So that is your Pset 3 solutions. We'll see you on the next video. Thanks. Bye.